Hey everyone. Um, we're going to be presenting over our launch vehicle landing controller comparison project for this AE6580 class.
Hey there. My name is Justin Femino. I'm located in San Diego, California, so you probably haven't seen me in class at all this semester. I work at Northrop Grumman as a GNC engineer, and I got my undergraduate degree in aerospace engineering at San Diego State University.
My name's Austin Wohleb. I'm out in San Antonio, Texas. I am a robotics engineer for Southwest Research Institute, and I got my undergrad from the University of Kansas in mechanical engineering.
I'm Jinha Kim, located in South Korea at the moment. And since I graduated in aerospace engineering for bachelor, I'm serving for military service in the Air Force as a jet pilot. Next.
We're going to open up here with an introduction to our problem statement, which is the vertical landing of a launch vehicle on the moon. Our goal here with our presentation today is to implement several control algorithms to control the vertical descent and achieve a steady hover state above the ground, and then compare the performance of those algorithms. Why this is important is today landing launch vehicles has become really the next modern day problem of space industry, as many companies are hoping to bring down the cost of their launch vehicles by increasing reusability, like SpaceX does today. In particular, NASA needs a working launch vehicle capable of vertical landing for the third Artemis mission on the moon.
As you can see, this is our system description. Show the model for simulating 2D rocket landing dynamics. We're modeling the rocket as a rigid body in the XG plane, and the vehicle has three main control inputs. As you can see, the rocket acceleration dynamics. We have main thrust Fm and the thrust vector angle pi, and the reaction control system FRCS. And as you can see, is highly coupled with these dynamics. And next, this is our sixth state. So we do have the horizontal position and velocity x and z dot, and vertical position z and z dot, and orientation theta with weight theta dot. These are our six states, and also we assume a symmetric mass distribution initially and update the moment of inertia over time as fewer mass consumes. So this is our setup. And also we put the limit FM, FRCS, and also pi for simple limit from -10 to 10 degree. And these are higher than linear due to a trigonometric coupling and time varying mass as fewer burns. So our main objective is to optimize the fuel consumption. Next.
So the first main controller we looked at was SMC control, which is sliding mode control. In short, this is a nonlinear controller method where a sliding surface is defined for the system states to follow. So it's the controller's job, if the states don't exist on that line, to push it towards that line. So this helps nonlinear dynamics behave like a first order system. And it is a well-proven control method that is considerably pretty robust. The only big issue can be chattering, which means that the system states will bounce back and forth, but there's ways to combat this. So for this study, I started with the dynamics that we already showed you, and then introduced a tracking error. But the nice thing about with this study is that all of our desired states are just zero. And so that kind of simplifies things. And then introducing the switching sliding function. This is kind of that line that we want our states to follow. And as you can see, it's based off of a gain and then the error and then the change of error. And then we can, from there, figure out our, calculate our controls functions. And this kind of uses a combination of everything above it. And this specific one uses the SGN function, but This just computes like the positive or negative value of that function. And so that can often lead to chattering. And so I found out that replacing it with the hyperbolic tangent function improved this issue.
Next control algorithm that we looked at is nonlinear model predictive control, or NMPC for short. NMPC is used to predict the system behavior over a finite time horizon, and then at that point compute the optimal control sequence at each time step. Um, Once you compute that optimal control sequence, the first value of that is used as your current control input, and then on your next frame of operations, you will use that previously computed optimal control sequence as the starting point for your new optimization problem. Some good benefits from this algorithm is that the optimization problem that's being solved at each frame, it naturally handles the input and state constraints very well. It also allows for an arbitrary cost function design that's not necessarily limited to just your standard quadratic cost function. Some primary issues with this method is that the high computational cost makes the real-time implementation challenging on real hardware, actual functioning systems. As well as an interesting fact is that finding a control to optimize the cost function, just by getting a solution to your optimization problem, you are not guaranteeing stability of your system by that alone. And so other constraints need to be added to ensure that occurs. Next slide, please. So going over how this was applied to our system here, is we did use a standard quadratic cost function and minimize that over a finite time horizon, with the awareness that the design of this cost function can influence the stability of our system as a whole. In order to ensure that our system is stable, we implement a passivity constraint against the passivity output, which is just our velocity terms. And this constrains our input to the set of controls that will dissipate kinetic energy from our system, and that provides us stability. So some future work that can be done on improving upon this is we could optimize the parameters of the quadratic cost function to produce better overall performance metrics, as well as study the design of any non-quadratic cost functions that may be performing better, and potentially implement barrier functions for preventing a large theta value, which can cause issues. Next slide.
As you covered in the recent lecture as MRAC, our last control is adaptive neural control, and ANC is basically a way to use neural networks to run control actions, especially when you don't have specific model of the system. It has a strong benefit. It can adapt complex and certain dynamics with. So it can also run light enough to use in a real time, but also there are trade-offs. It's hard to enforce safety constraints, and also it needs a diverse training data to generalize without the generation error, and also performance can be sensitive to training data quality and rules design. And also there are some gradient can vanish, meaning that running shows down or fails completely. And this is a kind of classical problem in deep learning for long period dependencies. Next. So this is how ANC applied in my system. So after simulate for over time, backpropagate the Rose gradients through the trajectory to update NN up weights. And I used an NMPC as a desired trajectory and for running the 6 states for these neural networks. And then control output, I used the correction term, which is the main command to compensate for modeling error. Here, even though it is data-driven approach, I try to use some physics correction term to mitigate the errors, because there's some without physical correction, the rocket often fail to converge, or sometimes it reaches out the saturation error. So small prediction error in the FN and FRCSS and pi, which is highly coupled, can nonlinear drift in both an X and Z direction. So this instability would snowball. So to mitigate this error, I use some Sontag formula and backstepping control we cover in the class. Next.
So here is a summary of our results. So we have the three states plotted, their rates, and then our three controllers. So you can see on the right here, our big performance metric was the amount of fuel burned. So SMC burned the least amount of fuel, with ANC burning the most. Key thing to see here is that NPC has a lot of undesirable oscillations compared to the other controllers, which isn't super great when you have a lot of chattering. It uses more energy, and that can kind of be seen by the amount of fuel burned. SMC is definitely the smoothest control, as there's not much overshoot or oscillation compared to the other controllers. Though it is worth noting that ANSI did have some major struggles because it required reference data, which is kind of a limit of the study. As Jinha talked about, he only used NMPC for training data. So hopefully in the future, we could have more data that we could test that controller and hopefully get a better result from that.
Thank you, Austin. I think the big takeaway here is that SMC is our best performing controller, and if we were designing a real system, that we would recommend move forward with that. But when talking about future work, there is a lot of potential for improvements with the NMPC by investigating different cost function designs and looking into how that could affect our overall performance metrics, as well as reducing those oscillations that we see. Looking at our system as a whole, what we looked at was really just a 2D simplification, some relatively simple rigid body dynamics. And future work could consider including the third dimension of translation, as well as all of the rotational directions for simulating a full, realistic, and fully representative system. I could also test the controller in real life with rocketry hardware. In addition to that, we could, on top of looking at different control algorithms, we could look at different control input setups. So of course, we were limited to our gimbal angle, our reaction control thrusters, and our main engine thrust. Depending on where those are configured and how they're configured, that could have a large impact on the overall performance of our system, regardless of what control algorithms are used. So yeah.
And these are our references. Thank you guys for listening.
Thank you.